So hello everyone and welcome to the second lecture of second week. So in the last lecture we talked about what is the basic array distance concept given two strings as input, what is the dynamic programming algorithm that you can use to find out what is the array distance between these two strings. Okay, and remember we defined certain operations, certain array operations, and we gave weights or cost for each of these operations. But all these costs were equal. Okay, so if you are substituting a character by another character, irrespective of what are the two characters, the cost remains the same. Same goes for inserting a character, the cost remains same, and also for deletion of a character, it remains same. So in this lecture we will briefly discuss that is there any way in which we can try to discriminate between various sorts of added operations. Firstly, should we discriminate between various operations? Should they be assigned the same cost, or should we try to give different cost to different operations? Then we will also talk about the practical problem that given a query, so by query I mean a term that might be incorrectly spelled, how do I come up with a list of terms that were actual terms that should have been used instead of the incorrect term? So what is a good or efficient algorithm to find out all the set of terms that are within some array distance of, say, array distance of 1 or 2 of that query term. So starting with the concept of weighted array distance. So can we weight the array distance cost depending on what are the characters that are involved in the operation? So firstly, is it required? So do you think substituting A by E should have the same cost as substituting A by M? So what should it depend on? Okay, what kind of, so for example, there are certain errors that you make very, very commonly and certain errors that you make very, very rarely. Okay, so now suppose an error is very, very common. Should I assign it a higher cost or a lower cost? So think about it. What does it mean to assign it a higher cost? Assigning it a higher cost means that the added distance between the two strings will increase if that added operation is present. Okay, so that means the probability of obtaining the other string as candidate will go down if the operation has a high cost. But if something is some sort of added operations are very, very common, some spelling mistakes are very, very common, we would like to give them a lower cost so that the actual candidate have a small added distance with the incorrect word. Okay, so it is important to understand what kind of characters will have a lower added distance and what kind of character will have a higher added distance. So can we somehow give a weight? So this is the basic idea. So why do we need to add various weights to our computation? So the idea is that some letters in a language are more likely to be mistyped than others. Okay, so let us take some statistics. So this is a confusion matrix for spelling errors that were found in a corpus. So X is the incorrect character and Y is the correct character. Okay, so what this table is showing, how often in that corpus they found an incorrect X for a correct Y. So for example, if you try to read the table, the entry for the first row, the entry corresponding to AE, so that means how many times instead of the correct E an incorrect A was substituted, and that number comes up to be 342. Okay, so that means in the corpus 340 times and instead of E, A was written. Similarly, 118 times instead of I, A was written. Similarly, 76 times instead of O, A was written. Okay, on the other hand, if you see B, it never happened that a B was written as A. So that means people make the mistake of converting, or instead of writing E, writing A. This is a very common mistake. On the other hand, B to A is not very common. Okay. So you can look at this confusion matrix and you will find a lot of nice patterns. So one thing you will see is that the errors among the vowels are very common. So substituting I for E, E for I, A for O, they are very common. Okay. So they may be because the person is maybe not knowing the spelling, or so even if he knows the spelling, by mistake he is typing the other vowel. So this is also possible. Now there are some other kind of errors that you can see here that come because of the way keyboard are also designed. Okay. So you will see the characters that come very close in the keyboard. So sometimes you mistype them. Okay. So this is again a common source of spelling error. So for example, M and N are very close together, and they also sound very similar. So it is very likely that you mistake M for N or N for M. So these kind of errors are very common. So some errors come because some of the characters sound very similar. So like all the vowels or certain characters, and also some characters are very close in keyboard. So that is again another source of errors. So now once we know that some errors are more likely than others, can I use this statistic to design my weighting scheme? So as I said earlier, if some error is more likely, the added cost from one character to another character should be low, so that I can easily find what should be the actual candidate given the erroneous word. Okay. So a smaller added distance means that is more likely to be the correct candidate. That's why we will give a smaller cost to those spelling mistakes that are more likely, and a larger cost or a higher cost to those spelling mistakes that are not so likely, that are very rare. So yes, so keyboard design is again one thing that gives rise to many of the errors that we have seen in the previous slide. Okay, so you can try to correlate among the characters that are coming very close in the keyboard. So you will see that many a times people make mistakes in typing one character for another. So now suppose you have some data, and by analyzing that data you can find out what kind of errors are common, what kind of errors are rare, and accordingly you can design your weights for different added operations. So now once you have these weights that depend on the actual characters, you can modify your initial algorithm. Okay, so how can you modify your algorithm? So for example here, if you try to compare this with the algorithm that we saw in the previous slide, so the only difference here is that instead of giving a uniform cost for deletion, insertion, substitution, what we are doing here, so deletion is now conditioned on the actual character that is being deleted. Okay, so you will see di0 is di minus 1 0 plus a cost for deletion of xi. So what is the cost for deleting that particular character? Same goes for insertion. What is the cost for inserting that particular character? Even in substitution, you might have cost for, so the separate cost for deletion, insertion, and substitution of one character by another. Okay, and everything else remains the same. The only thing that changed is that instead of using equivalent cost for each operation, you are now giving costs that are dependent on the actual characters that are inserted or substituted or deleted. So that is my weighted added distance. So now, so what do you do with, so how do you modify your algorithm for taking care of transpose, for instance? Okay, so that was the algorithm where we had three operations. We had insertion, substitution, and deletion. There were three operations that we were using in that previous approach. So there is another very common added distance operation that is used, and this is called transpose. So that is, if I am transposing two characters, and you will see this is a common error that sometimes you make. Okay. So for example, so I am wanting to type AL and instead I type it as LA. So this is called transpose. So in general, if I write XY as YX, this is called transpose. Another name for this is metathesis. So now, how can I modify my earlier algorithm to take care of this case? So till now we have three operations: insertion, deletion, substitution. In insertion, I see the previous insertion, deletion. I see only till the previous word. Okay. But what do I do in the case of transposition? So the transposition, I'll have to. So because it is, you have to go 2 characters before. So I need to go to D in my cost matrix, D I minus 2, J minus 2. Yes. And suppose I give a cost of 1 for transposition. Okay. So I will write D I J as, so there are other costs that we had defined earlier, but for transposition I will say D I minus 2, D I minus J minus 2 plus 1, and what will be the condition? Only if, so the previous word in X, so okay, so I had defined my strings as X and Y here. Okay. So this is my string as X, this is my string as Y. So what will happen here? This is up to I. So this Xi minus 1 will be same as the jth character in Y. So if Xi minus 1 is Yj and Xi is equal to Yj minus 1. Okay. So if I find that, so X is still I, yes, and Y is still J. So if I find that the I minus 1th character of X is same as the jth character of Y, and the ith character of X is same as the J minus 1th character of Y, then I will say that this cost is D I minus 2, D J minus 2 plus 1. So again I will do a minimum of this. This, if this happens, this is my transpose. And then I have other conditions for insertion, deletion, and substitution. And that's how I can modify my algorithm, the initial algorithm, to also include transposition. Okay. So with all these operations, this is the only other operation that is also commonly used in computing at distance. So now, so we talked about weighted at distance and also about including another added operation like transpose. So as I said earlier, so we will also discuss briefly. So what is the practical scenario? So the practical scenario here is you are given an input word. Okay. So remember in the introduction slide we were talking about this error. Okay. Say World Cup, and by mistake I have written WOLD instead of writing WORLD. So now the practical problem here is, once I know that this is not the correct word in my vocabulary, how do I find out what are the possible candidates that might come in place of WOLD? So that is, what are the suitable candidates? Now as per our definition, so the suitable candidates are those that are having a small added distance from the actual error word. Okay. So in turn my problem is, how do I find out words that are within some small error, some small added distance of word? So now how do I solve this problem? Given a word like WOLD, find out all the words that are within a distance of say 1 or 2. Now one simple thing you might say is that I will list down all the words in my vocabulary somewhere. Okay, so I have all the words in my vocabulary starting from W1 to Wn. Okay, and I'll find out what is the added distance of W1 with volt, W2 with volt, and up to Wn. Okay, I'll find out all the added distances, and then I will, among those, I will choose all those that are coming up to be very, very small at distance, some top entries that are coming out to be within a small added distance. So I'll find out a set of entries. Okay, this is my candidate. So but you can immediately see that this may not be a very, very efficient solution. Okay, because my vocabulary size can be quite huge, and I have to find out added distance from this to each of the words in my vocabulary. So that will be really, really time consuming. Okay, so instead, can I do something more efficient? So one simple thing is, I should try to search in an efficient data structure for searching all the words in my dictionary. Okay, so in case you do not know, so one of the very efficient data structures that is used for searching the strings is called the trie structure. Okay, so using the trie data structure, you can do search efficiently in the linear time. So linear in the length of the input string. So I am giving you one example here. So I can use a trie structure. So idea is that, so you take any word, you can start from the initial root node of this trie structure and keep on following the arcs, and in the time linear to the length of your word, you will reach to a node and find out if the word is available in the vocabulary or not. So by that you will be able to search all the words in the vocabulary. And this trie structure can be used efficiently for computing the distance of any new word with a word in this trie. So this is one possibility. But this again, it requires you to do a lot of computations with respect to all the words in your vocabulary. What can be other possibility? So other possibility, if you think, would be, so instead of trying out to find out the additions of this error word to all the words in my dictionary, can I start from my error word and try to enumerate all possible words within some added distance. Okay. Say 1 or 2. Okay, I am trying to enumerate all the possible words in additions 1 or 2. So I will find out the word like W, R, L, D and everything else, and then I can have a further check to see if these words are there in my dictionary or not, and there I can use maybe the trie structure, that whether these words are available in my dictionary or not. So this can be other possibility. Now what is do you think this will be efficient, this approach? So let us see some numbers. Okay, so yes, so I can possibly generate all possible terms starting from the error word that are within some added distance of less than or equal to 2, and there I can take care of all the deletion, substitution, addition and transposition. I can try to take care of all the possible added operations. So starting from WLT, I generate all the possibilities with added distance of 2. Now, so if you just try to do say simple math, try to compute how many different possibilities you will have to explore. So let us see. So suppose if you take a word of length 9, that is 9 characters, and suppose you are taking a language like English, an alphabet is 36. So 26 plus other characters, and if you just do that, so this will give you roughly 114,324 different possibilities to explore, starting from the word of length 9. In which of the 4 you think will give you a lot of possibilities? Okay, deletion will probably not give you many possibilities, but substitution will give you a lot of possibilities, and insertion should also give you a lot of possibilities. Substitution, you can substitute each character by any of the 36 characters, so that gives you a huge number of possibilities. So this is again huge number. So starting from a word of length 9, you are going to explore 114,300 different possibilities. Okay, but yeah, English is still okay. So we have 36 characters. So think about a language like Chinese, where the alphabet size is 70,000. So you can't even think of applying an approach like that. Okay. So this is an approach that is slightly better than before, but it may not be very efficient again, depending on the alphabet size. So what can be other possibility? Okay. So other possible algorithm is that the idea is that all these added distances can be attained if you try to do a symmetric delete from the current word and the possible candidate words. Okay. So all the added distance of operation 2 can be found out just by doing deletes in both the words. Okay. So what is the idea? So this is called the symmetric delete spelling correction. So idea is that from your query word, and so from your query word you will try to find out all the words that come up within delete of 2 from the query word, and from your dictionary for each of the words you will try to find out all possibilities that come within an addition of 2 as per only the deletes, and this will cover all the possible variations with additions of 2. Okay. So we can take a simple example. So suppose let's take the same example of WOLD, or so even we can try to take a different example, say WOTLD instead of WORLD. That is the correct word and this is the error word. Okay. So what you will do in symmetric delete operation? So this I will do offline. So in offline, starting from world, I will store all the possibilities within additions of 1 and 2. So I will store with world that there is a word WOLD that comes up, WORD, and so on. And from these again you will have, this is delete 1, and you will also have again other candidates for delete 2. At runtime, when you get this query like WOTLD that is incorrect, you will do the same thing. So this is at runtime, and you will again generate all the possibilities with delete of 1 and 2. So we are taking here 1 only to show the possible thing. So you will find WOLD, WOTD, and so on. And now you will try to match if one of these is available in this dictionary that is built by this semantic delete operation, and you will find WOLD and WLD is a match. And once this is a match, you will go back to the original word and then confirm that this word and this word have an added distance of less than or equal to 2. Okay. And that's how you can find out all the possible words within additions of 2 without having to do a lot at runtime. Now can you tell why? Because you are only doing deletes at runtime, and deletes are not many. Okay. So if you do one delete, if you have a word of 9 characters, you have only 9 possible deletes. So this is not very inefficient at runtime, and this all is done at offline. And later you will have a further check to see that these 2 words have an additions of 2 if your 2 is your threshold. So yeah, if you take number of deletes of 2 for a word of length 9, it will be at most 45. So this is not a very big number. So this is one approach that you can use for finding out all the possible dictionary terms within some added distance efficiently at runtime. Okay. Yeah. So now, when we have talked about added distance and some variations, so we will now focus on this task of spelling correction with which we had started this module on added distance and all. So So when we talked about spelling errors, there are two kind of errors that you might have to deal with. So one that are easy to handle errors, so I'll say slightly easier, they are called non-word errors because they are easy to detect. So the erroneous word is not in my vocabulary. So in this case, so erroneous word is BEHAF, that is not in my vocabulary. I can detect this is an erroneous word, and my task is to correct it to the actual word BEHALF, behalf. And this is also called non-word error. Okay. What is slightly more difficult is something called a real word error, when the word that is in error is also in my dictionary, but somehow the user has misspelled to a word that is in my dictionary. So here are some examples. It's like typographical error. So instead of writing there, somebody has written 3. Now 3 in my vocabulary, so it is not easy to detect that this is an error. Now correcting this is called a real word error correction. Similarly, there can be something for because of the homophones, okay, because of say peace and peace, the two different variations of peace, you might misspell very easily, and TOO and TWO is very common error. So they are also called real world errors. Now to handle both of the non-word error and real word error, you need to use various probabilistic models, okay, and this is what we will be focusing. So in non-word spelling errors, so non-word means the word that is not in my dictionary. So any word that is not in the dictionary is called an error, okay. And so for handling this problem, it is better that you have a very good lexicon that tells you all the possible words in your lexicon. And this lexicon may also be dependent on the particular corpus that you are processing, okay. So for if you are processing scientific corpus, you might have a different corpus than if you are processing a news corpus. So you should know what are your words in the dictionary, and when you encounter a word that is not in your dictionary, you will treat it as an error case and try to correct it. So in general what you will do in non-word spelling correction, so starting from the error word, you will try to find out candidates that are similar to the error word. And how will you define the similarity with respect to the error word? So you will say the words that are within some small added distance, okay. That can be one possible criteria. And if you are using noise channel model, that will be the topic for the next module. So you will say the one that is coming out to be as per the highest noise channel probability. So this will be your candidate words. So you will choose some of the candidate words like that. On the other hand, if you are dealing with the real word spelling error, you will try to find out. So now you do not know in the sentence which of the word is actually erroneous. So what you will do for each word, you will find out other words that are similar in added distance or some other criteria. But in the candidate, you will also include your actual word. So TWO is there, so you will include TWO also with TWO, and you say that the actual sentence might contain any of these two words, okay. And then finally you will try to maximize the probability of the sentence using some noise channel model. So this is what we will be discussing in the next lecture. So where we will talk about noise channel model in detail and how it can be used for doing the task of spell correction.